Good afternoon. This is a presentation about one Martian year survey done by ACS MIR instrument on board ExoMars trace gas orbiter mission. So what is ACS MIR? It's a part of ACS instrument. It has three scientific channels, each one dedicated for its own spectral range, its own scientific goals. For example, thermal infrared here is mostly to do the nadir observations and then retrievals of the temperature profiles. Near-infrared channel, based on OTF and HLA, is working around 1 micron, mostly measuring water vapor and CO2 profiles that allow to retrieve temperature and pressure. And then the third one is middle infrared, which is covering the range from roughly 2 microns to 4 microns. It is of special interest because in this area of spectral wave numbers, there are a lot of features, absorption features of gases that are either already measured in the Martian atmosphere and require some further scientific investigations, or are not measured at all, and we need to place an upper limit or measure them precisely for the first time. So I will not go into details about the hardware. I will just say that we're not measuring the whole range at once. We're actually doing a window by window with the secondary grating, secondary diffraction grating. So at once we're actually measuring only a portion of the whole spectra, for example, like so-called position 12, let's say. And by doing that, during one occultation, we're measuring this range of wave numbers. So it's filled, actually the whole range is filled with features of CO2, of course, which is a lot of it in the atmosphere of Mars. Then a lot of CO, a lot of water vapor indeed, and HDO. Also, apart from that, we can trace features of different species which are listed here. Methane, of course, for the first in the first place. Then different things that can originate from methane, like H2CO, chlorine species, HCl, and OCS, sulfur species, yes. So all that is actually covered. All that being measured from 2018, so more than 2 terrestrial years and more than 1 Martian year. So we have quite a big statistics already collected. This data is being processed. We do have certain improvements, of course. And I will start from methane, of course. This is work led by Franck Montmessin. The paper is in preparation. So in the first months of the mission, we had a first paper, Korablev 2019 in Science, with a non-detection of methane. It was in a contradictory with MSL measurements on ground. But now we still stand of that at the altitudes we're sounding, which are from 10 to 30 kilometers, where the sensitivity is the best in solo occultation mode, there is no methane, and our upper limits are an order better than the MSL measurements on the surface. Of course, it depends a lot on the season, on the dust load. When there is a lot of dust in the atmosphere, we see the upper limits we see are worse, but sometimes we're reaching values like 10 ppt, which is quite a small number, and no signs of methane. One can say that maybe you're measuring in the wrong place, and indeed, coverage, the latitudinal coverage of our occultation is mostly at high latitudes. But still, we do have a number of occultations close to MSL locations, close to Gale crater. It's quite dusty there most of the time, but still our upper limits are lower than the MSL measurements. So this paper is in preparation, but this is where we stand right now on this topic about methane. Recently, HCl was discovered to be present in the atmosphere of Mars, and surprisingly, it was found to be present only at a certain season, at the perihelion season, where it's often dusty in the atmosphere of Mars, and when the water is rising at high altitudes. So all that is leading us to a conclusion that there is a correlation between HCl originating and the dust and high water in the atmosphere, but this is not yet solved completely because the chemistry, the atmospherical studies are ongoing to understand why it is there. So paper is accepted to Science Advances, and several more papers are actually being prepared and submitted these days. So for other species, in 2 words, what is being done? Previously, we've been checking only the best, I mean the cleanest orbits with the smallest dust load to get the best sensitivity. Now we're using bulk reprocessing of everything, just to check maybe like HCl, some species can be present and then disappear. The retrieval algorithm is based on Fedorova, Anna Fedorova's work, described in the paper of 2020 and then reference within. So it's 11 Berg-Marquardt, 8 iterations, and then a Tikhonov regularization to make everything smoother. Certain work is ongoing with carefully stating the sigmas, the error bars of the retrieval values, because they define actually the upper limits of our results. Okay, on the example of so-called position 11 and diffraction order 174, that is my favorite because it has plenty of things there. So it can be used to measure the HCl, the OCS, the NO2. So all that is actually in one order, which is great. So we're using several lines from the detector because every diffraction order is actually a stripe on the detector, not a single line. Then we can use the solo lines and the lines of the known gases to do the fine tuning of the calibration of the wave number pixel calibration. The ILS is not being tuned, unlike other works on ACS MIR, because the lines are very weak, so the ILS tuning is not done. And the temperatures and pressures are taken not from the model, but from the measurements by ACS MIR that are always together with ACS MIR. So 2 channels are measuring together. That is a certain advantage, of course. We can use that to do the cross checks, the validations, and to get the temperature and pressure from another instrument. So here, it's not necessary to take the whole range, actually. We can do the windowing to increase the sensitivity. For example, here, it will be 3 gases, H2O, NO2, and H2SO. And then here, for example, we can take another ones. H2O is always there, more or less, when it's wet. The other species depend on the season. The OCS not yet detected. So example of the retrievals for H2O and HCl, which gives these 2 species give a value. So the HCl profiles, I will not go into details because it's not published, although presented during the conferences, but that's not the topic of the talk, so since it's discovered and present. But what's important to take here that on the bottom plots, it's the sigma, so the error of the retrievals. And you can see that it's reaching the minimum values at certain altitudes of around 15, 20 kilometers. So this is the area of our best sensitivity. This is just important to keep in mind that when we state an upper limit, we're actually referring to a certain altitude in the atmosphere. And this altitude is also changing with the dust load. But in general, the lower the better. I mean, when this altitude of the smallest sigma, it should be the lowest. Okay, now for a species, OCS. So sulfur-bearing species, what we can do is we can do SO2, H2S, and OCS. And if we would see them, we would say that, okay, great, there is a volcano on Mars, never found before any volcanic activity. But for the OCS, we're not seeing anything. The distribution of the values, positive and negative, is around 0 quite nicely. We do increase our current knowledge. We increase, but we decrease the upper limit. So we say that it's not 2 ppb like in Hayat 2017, but now it's down to 0.3. Next thing to be said is that if we assume that we're searching for volcanic activity, we should actually look for not OCS, but for things like SO2. From the terrestrial volcanoes, we know that OCS is only a very small portion of the outgassing, and the most is SO2, water vapor and CO2. Well, water vapor and CO2 are always measured on Mars, but SO2 never before. So we should keep that in mind during planning and measurements. Next thing is H2SO. Since we don't see methane, it would be strange to expect H2CO, but it's worth checking. But like for OCS, it's not there. Again, we're improving our knowledge by a factor, roughly. And I don't know what else to be said here. Just it's not present. For the NO2, a story could be slightly more interesting because from the models, we expect that NO2 should be there, values of about 0.1 ppb. Our current knowledge is much higher, 100 times bigger, 10 ppb. What we are measuring currently right now is also very noisy, so we cannot say that, yeah, we have a detection, a quite nice fitted spectra, but we're getting there. So the median value of the most accurate retrievals is actually 0.1 ppb, so it's the same as expected. Now we are putting additional effort in calibrations, mostly in co-aiding things, to get a good detection, and by that we could then publish this result. Some other stuff worth mentioning for this is HO2, which is also believed to be there in that atmosphere, especially during perihelion season. We are covering the wave number range where it should be found, but well, we don't see it just because the expected values are very small, and the HO2 lines are covered by CO2. Well, in all that math, it's hard to do a detection. Then phosphine, we were inspired by recent Venus publications and all this activity. We did check the Martian spectra around 4 micron, but we stayed on the upper limit. Must be said that phosphine was never actually considered as a science goal for Mars, but we checked it. It was interesting. Then for the SO2, I'm returning to sulfur. We're stating only an upper limit, and we're not competing here with other works based on submillimeter spectroscopy. But our benefit is that we can do irregular measurements, and by that we can probe the atmosphere, and we can check, and we would catch if some activity would happen on Mars. Summary: methane is not found still. We don't see it with a very good accuracy, and we're going to stand on that. For the other trace species, we're plus minus an order better than the previous knowledge for most of them. HCl was discovered to be periodically present, although people were predicting that because chlorine was found a lot in the surface. But still, this is a very nice positive discovery. Phosphine is not on Mars, and that is not a surprise, but just was worth checking. The primary goal now is NO2 measurements because we're close to the predictions of the models, and we of course continue working, and the instrument is in a good shape, so we have things to be done. Thank you.